Supervisor. Oh, that's laughing. Oh, yeah, of that. Hey, Niranjan, hey, Venkat. Oh,
Hello.
Hello.
yeah, we'll be more punctual, I think, from next week. Yes. Oh, starting Monday, so it's yeah. Hey, yes, nice. Yeah. Okay. Yeah, any questions on what we did last time? Anything general? So we did meet on Wednesday and that went well. So, but that was between us, and I think that is also going to be regular. And there was an advice that I should make this unlisted, not even today's lectures. I should make it unlisted, not public. So I'll make it unlisted. Currently, it's all public. The playlist itself might be public. That's convenient, I guess, but the videos will be listed, so it won't come in the search. So yeah. So we were talking about response functions.
Did you speak?
It's recording. This main idea is we have some function PSP getting affected but by something else. So prime susceptibility is a good example, but this doesn't have to be that. It could be in principle any function. And in general, this is a vector. Polarization is a vector, but I'm treating it as if it's a scalar. And for dimensional reasons, I should also have an epsilon naught here, right? So there should be an epsilon naught here, but I'm not going to write that here. This is just a point. E and P is being written just for the sake of it. So we have minus infinity, and for causality, we would like this to be in here. Before we proceed forward, we said let's look for a step function. But we wanted to go to Fourier space. And step function is e, 1 greater than 0, 0. And in the Fourier space, we argued that this looks like a delta function at omega. If this argument had omega minus omega prime, this becomes the argument shows up here also. And this one is the plus sign. Plus I omega over omega plus delta square. Everywhere you see a delta, it should be understood.
Omega square plus delta square.
Yes. So,
Can we zoom it a bit?
so it is not visible. No, we cannot zoom in. I have to write bigger.
We can zoom in by this way. Like, tell me if it is better for you. Is it better? Or still not?
Very slight change.
So yesterday it was quite nice, right? That we were in a farther place.
Still small, Venkat?
Yeah, I cannot.
Slightly better, yeah.
Then you write bigger, Shajesh. So Shajesh will write bigger, okay?
Sure, thank you.
Yeah, at least make it 1.5 times 1.25 times. Okay, Let's go.
So. So look. Oh no, expensive. Yes. Is this better?
Yeah, good, good, good.
So you know what size. That's better.
Okay, so. Yeah, so the idea would be to use this feature somehow in this place and say that your P is equal to minus infinity plus infinity. So now I'm removing the causality which was explicitly put in there, but now it is inbuilt in here. And if I'm not going into Fourier space, it is inbuilt in the following sense that P is being imagined as product times let's say. So very soon we want to have a intuitive feel for what these pieces are. Chi is the total susceptibility. This is of course a step function, that is where causality is coming in. And f of t is the susceptibility if causality is not taken into. So you will see f showing up here and there. So we want to have a feel what f is. So that is the susceptibility in the absence of causality. If you let's look at Fourier transforms of some functions, or at least one property or two properties actually. One is of course step function we already talked about. Let's say what if we have the chi is real. So let's say.
Let me ask you a silly question about
Yes.
Fourier transform.
Mhm.
I mean, generally, if it is t comma t prime, I will have exponential of I omega t and I omega prime t prime, like two different functions, right?
Yes.
And so whenever we are doing in this translational symmetry way,
If it is t minus t prime, this is t minus t prime, this is t minus t.
no, not because like I'm saying, next thing you will do is like Fourier transform this, right?
Yes.
So t minus t prime will be treated as one variable, and then t prime is treated as.
Let's see how else can we do. Yeah, so maybe that's where we can start from. So a few things. Maybe let me list it here. I don't know how much space I have. Maybe on the right side. Yeah, I'll erase this out. So I think non-locality, if I were to call that, so the integral. How does it look like in the Fourier space? Second is a step function we already talked about. How does it look in Fourier space? Third one, if it's a real function, like most of the electric fields susceptibility, polarization, all three are real. If you have a function that is real in Fourier space, how does it look like? What in Fourier space will we look for that feature? And a step function here pretty much says that it is whatever exists on the right side is 0 for t less than 0. Which pretty much says that I can put anything for t less than 0 for function and still it's the same. Like there is no information about t less than 0 there. So often what you do is you use it for your advantage. You say that f, I will choose it to be a real or sorry, a even or an odd function. I'll put in some symmetry there as per my convenience. whatever is needed. It should not affect any result, so that's another exercise that you should come back and say that, oh, did that choice disturb anything? But that's for another play. So I am going to put the condition that f of t is odd, and then you should know what feature shows up in the Fourier space in there. So we will look for suppose a function is odd function in time space. How does it look like in a Fourier space? So these are the features we should know. Let's start with the first one, non-locality. So let's Fourier transform this thing in the Fourier transform this equation in the how does it look like in the frequency space, right? So I'll start by saying P of omega, right? So P of t is P of omega. Like Fourier transform of t will be P of omega. Many ways of doing it. This is one way. Cos infinity, and this is the dt exponential I. No. Right now, P of t is this. Substitute that in there.
Yeah, I'll get back to it. I got like slightly confused again. So the theta function inclusion is telling that when t is greater than 0,
Yeah, this is
then
f,
it
this is f of t. If t is greater than
Yeah,
0.
yeah, yeah.
And it is 0 if t is less than 0.
Yeah, I'm just not able to wrap my head around negative infinity to t here for a second.
But here, this one even. I think the point is I would like t to be greater than t prime, right? T is the upper limit.
Okay,
So t has
t minus
t
t prime
minus
is greater
t
than
prime.
0, okay.
Has to be greater than 0, right? That's the condition for causality.
Mhm.
So if I want,
Yeah,
only then it should survive, basically. That's the idea, right? So
Mhm.
that's got by
Which is what it is doing, yes.
right here.
Mhm.
So I think the confusion is suddenly you see that t here is t greater than 0, that might be the confusion. But that's coming from this feature.
Okay.
Okay, so just substitute this in. Infinity t here is to I omega t, p of t substituted. And we have dt prime. Yeah, let me do it in multiple steps if you don't mind. Fourier transform again. Fourier transform chi, this will be the omega, but I have already used omega on the left, that's a free, so let me call this d omega 1 over 2 pi. Here it's minus I omega 1. So this is what you were asking, Brian, t minus t prime. This automatically comes as t minus t prime. So the Fourier transform is in omega 1. When I'm Fourier transforming that's t or t minus t prime, I don't have any choice. Right, so this is chi of omega 1 now. Take this goes to your question.
Go next.
And the exponent electric field is, I think I can squeeze it in maybe, minus infinity e omega 2 over 2 pi. Exponential of minus I omega 2 e prime. Oh, did I get smaller again?
I think so.
Venkat?
Yes, a bit, yes.
Hey, can I survive with this equation or should I rewrite?
Yes.
Thanks.
Yeah, so basically you treated t minus t prime as one variable.
One variable, yes.
what will something change if I end up choosing yeah.
T comma,
No, not T comma T prime. Suppose with a translational symmetry here, which is what T minus T prime is. No. With this kind of construction, when T minus T prime is there, can I still go ahead and choose two exponentials for showing? So I take I omega 1 T and I omega 2 T prime.
I see what is, yeah. Probably one of them will become a delta function in video if you want to do that. So I think Raj's question is I of T comma T prime.
No, I'm not. I'm
If it
still
was
wanting.
like this versus this, right?
That is clear. That we know we can use two of
So I'm
them.
going to do this one as if I'm doing this.
Yes,
Right? That's what
yes.
you
But
want.
write it in this equation, not in that equation.
I want to know what, let me do it.
I'm asking you to do a mistake deliberately. Okay,
Okay, I'm a little confused here. I want to practice.
yeah, go
a
ahead,
bit.
practice.
Yeah, first. So this is d omega 1 over 2 pi e raised to minus I omega 1 t and minus I omega 2, right?
Oh, I'm sorry. I will.
T prime and chi of omega 1 and omega 2.
So if you were to write it in this one, you might have, or I might say that I can write it as chi of omega 1 minus omega 2. Will I be wrong in saying that?
I think the point is when you do it here this way, if you want to do it in this form here, or yeah, I think this is not the way I should have done this. I should write this as phi of t minus t prime and t plus t prime. I should write this in two variables. Remember the integral that, so we get this delta of 0 there?
No,
That's in
Shailesh,
the-
you are getting guided by an answer here. I am trying to tell you that make a mistake. Like, what does actually T minus T prime represents? Why it is written as T minus T prime? Why cannot T comma T prime?
Because t plus t prime is not there. That's what I'm, now that I kind of see that point, I can say that this is a one variable function. In many ways. In this sense. So give me a second. Okay, how about this? I'll go back, right? So you want me to do this again. So I say this is equal to chi prime of t minus t prime and t plus t prime. I think this is good. Okay. And this will be equal to e omega 1 over 2 pi t raised to I omega minus I omega 1 t minus t prime. And like even the limits here, one has to be careful. I think the Jacobian might give you some factor of 2. I'm not sure. If you allow me this thing. So e raised to minus I omega 2 t plus t prime. And now this pi of chi prime of omega omega 1 and omega 2. Right? If this is independent of t plus t prime, then what happens? So this is fine here. Delta function. Okay, let's see. Okay.
There is still some kind of integration somewhere, right?
Yeah.
If you go back.
Yeah, I think this is what if this was not there, okay. If this was not there, what do I get? That's equivalent to omega 2 going to 0. Yeah, how do I kill this t plus t prime equations? If omega 2 is 0. No.
Like, so if you will want to have a dependence only on one omega, not on two omegas, then you will have to have an integration on either t prime or t. That will give you the delta function, which might set your omega to something.
Yeah, so I wrote this down pretending this is there. So now if this was not there, what do I do here? I'm confused. I need t plus t prime to be not there, right?
Like at this equation, this point, you cannot do anything. Like unless you introduce a delta function. But if you want to bring out a delta function, then you have to write that my left-hand side, I demand it to be only chi of omega or chi of omega 1. Like it has to depend on only one frequency variable, which will require you to do an integration on one of the time.
But if I say there is no omega 2, for example, correct? That still leaves me with a delta function, right?
How
So
would
that's not sufficient. So let's say for a moment that this is not there. That just doesn't give me t minus t prime alone, right? This is delta function. This is delta of t plus t prime. But we don't have that. So we need a 1, right? 1 is equal to. So we need a delta function here. Yeah, maybe. I think in the Fourier space, this will look like. So this will be chi of omega 2 times or omega 1 times delta of omega 2. And that's 1, correct? So delta function, yes. So this is now equal to minus infinity to 1 plus LC. This comes out pi of omega 1. This is what I used there, right? So delta omega sets this to 1 and maybe a 2 pi. Because of 2 pi. So yeah. So your answer to your question is if t plus t prime, if I want to keep it in this form, then the second frequency is contributing only a delta function.
I guess yeah, okay. This is you added to something, but what I was asking is that like take t minus t prime, is still go ahead and Fourier transform it as omega 1 and omega 2. How would you proceed in that fashion? And what would you be doing wrong?
I think that will be wrong here, right? Because then there will be omega 2 there. And I know that's wrong, so I don't want to write it. You want me to write it, but I can write it if you want. So you just say, you find the help, like Seth and Jackson, I suppose. So I don't know. At my price. This is what you say, I guess.
Minus. Or yeah, negative,
Yeah, right.
right? Yeah, negative.
And then I don't know what to write. So you would say chi of omega 1.
Exactly, that's what I'm asking. What would you write? Why can't I write it as omega 1 minus omega 2?
It's not.
Why?
Okay, maybe
Why
let's see.
not?
Okay, let's see. Okay, yes, well, you want to write omega 1 minus omega. Okay, yeah. You're saying omega 1 minus. Hey, everything has to fall, right? It's not become, right? Whatever we do.
Yeah, so that's exactly my question is, what are you doing
Yeah,
wrong here?
there I was right, whatever we want. Okay, so let's see. So you're
Like you
saying,
would like this to look exactly like that one. You would like it to show chi of omega 1 only.
so. Because if omega 1 was equal to omega 2, yeah, that's not what you want, right? Then this will be, oh, you want comma then, right? Probably. Comma. Yeah, because if it was minus, then omega 1 is equal to omega 2 is when it happens. That will make it 0. Yeah. Well, I don't know. Let me escape. I don't know. Okay. Okay.
Okay.
Sorry.
No,
Yeah. I don't think I'll get lost maybe.
so it always bothers me about the susceptibility functions, that why on earth they are forced to be written as t minus t prime.
That's for the locality that you want.
Exactly my point. So, I mean, is it not no other way of reaching it?
No, no, how about this? Okay, let us say that it was not t minus t prime. What that would mean is that it depends on t prime. Let's say today I'm using a material. I have some properties. If it is not t minus t prime, that means it's not translationally symmetric. It means that tomorrow when I come back, my equations have changed. Right? That's what it means. If it's not translationally symmetric, my equation, Newton's law is going to change on a date basis. If it's not translationally symmetric.
Yeah, but then you do not make it translationally symmetric for entire time. You force the causality into it. I mean, you do realize that this function creates a headache.
No, this is the
In
nice.
the theory, because of that, you cannot write electromagnetism as whatever we struggle with writing
Yeah, I
electromagnetism.
think it is a causality that comes into picture. This is the nice part where in frequency space it is decoupled. But then we have this feature again. Now notice this is local, right? This is T, T, T. You would think this is an easier function, but now you go to Fourier space, this will spread into frequency. So this is the price we will pay that, okay, in a sense, we would like it decouples, but then again, the moment you bring in causality, it will again couple. So let's see this.
I mean, I know how it will proceed.
Yeah.
It's just like it has always been an annoyance, chi of t minus t prime.
Yeah, so probably I will separate it a few things, maybe at least.
Yeah, I mean,
Clear.
let's proceed. I've been giving hard time to Shajesh in a different problem too. But I guess like it is always for me to go back and like look at things. Can that be done differently? And I don't think it's
I
easy.
think she's expecting you guys to do the same because you have to be critical. That's what she's saying. You're not.
Like question everything. Why believe anything? So bigger writing, bigger
Okay.
font.
Oh, bigger font. Yeah, next one. Yeah. So, and by the way, most of the times, at least in field theory, we are going into Fourier transform. This is the standard thing you go. It's the same tricks you will use. You really don't do any Fourier transform. You only interchange integral, and we're not performing an integral. You're just interchanging integrals and bringing back things, Fourier transforming back and forth. That is all. At least it seems like that. Sorry. Okay, so now I want all this in Fourier space, so I'll move the time ahead frequency later. So is this big? Yep. Again. Frequency is I of 1. Now all the times. So this is T. So there are 2 times. And they'll collect all the E's. e raised to e omega. So this is omega 1. Let's just be fun.
What did you write? Omega? Yeah, okay.
Omega 1. Is it readable on the other side?
Niranjan and Venkat, please
Yes,
keep.
yes.
Yeah, it's clear.
Okay. Yeah. Okay, so two are now doable integrals. This is 2 pi delta omega 1 minus omega 2. So that means wherever I see omega 1, set it to omega 2. And this integral doable again, if I omega minus omega 1. So basically you're setting all frequency to omega, that's all you're doing. And there are two delta functions, so I can do two integrals. So that's the omega 1 and omega 2 integral. So one of the integrals sets omega 1 equal to omega 2, the second integral sets omega to the frequency. So this is practically telling you this is chi of omega times u of omega. Right, so yeah, whenever we have this kind of interaction, if you want, in Fourier space, it is algebraic. Like in a sense, this is kind of 2 points or many points here becomes a single local in the Fourier space, and that's what those are the places where it will be helpful. That's one thing. It's the other way also. If, for example, if I were to do this in Fourier space, it will become the exact opposite. It will become an integral on the frequency space. So we have to deal with that. So you will see that whatever integral comes in, that's because of this. This is local here, non-local in Fourier space. Here, this is non-local. Yeah. Okay. So that's I would say I was going to list a few things, right? So we said this is the locality. I think it's called locality. Second is step function also we talked about. Let's quickly do the reality. So what it said function is real. How does it look like? And I'm going to erase this. I'm not going to copy this. Like ideally want to keep this on the right hand side so that I can refer back, but I don't think I have enough floor space. Okay, so next, let's say if a function is real. I have a function p of t. P of t is equal to step, right? So that is so this is complex conjugation. I think in different, I myself in different places use different symbols. This is star means complex conjugation. Sometimes it is bar. Sometimes it is dagger. Maybe I don't know. Different places. Okay, so let's Fourier transform both sides. So this is minus infinity to plus infinity d omega over I exponential. Yeah.
What will go wrong if we had a complex function?
What will go wrong, but we don't, I mean, that will be added baggage, right?
Like, is
What
the constraint that we do not observe it?
Yeah, like physical quantities are real. Complex quantities sometimes have nice symmetries, so there are a lot of advantages to complex functions. But in this, we don't. Actually, we do the susceptibility when we at the end whatever we do, it is done in a complex space, so there are quantities to that.
Do you know of any example where if the quantity was not complex, it will not, or any complex feature of a quantity shows real effects? Or in a,
PT symmetry. Is that what you had in mind?
no. I was really thinking if there has been any kind of a proof on something which says that, oh, if this was not complex, you will not see this effect at all, and which is observed also.
Yeah, that's going against the PT symmetry philosophy. PT symmetry says that anything that is complex, you can simulate it using PT symmetry. Isn't that right? Not sure. I don't know.
Yeah.
Good point. Yeah. So yes, again asking, is there a complex function?
Like for like, let me give another example, like counter example. We talked about this Aronoff effect, right? Which is
Yeah.
non-existent, right? But you see a measurable effect of that thing.
Yeah.
In the
That's
similar,
complex.
in the
That's
sim,
because of the exponential, right? I don't know whether it's complex or not. It's a phase.
in the same way, like, I mean, do we have anything ever talked in terms of, oh, this will not show?
But
or
why
measure-
not? Now that you give it, you yourself gave an example. I don't know where.
I still don't treat it as a complex, but yeah, everything will be complex if you go by quantum mechanics. Like we talk about probabilities, but all the amplitudes are complex. Anyway, let's not go there. Let's stick to real functions. And again, my goal or cross questioning is arising from the fact that reality and causality, which gives you the Kramers-Kronig
Yeah.
relation, are a nuisance. And let's proceed with that.
Yeah, it's a nuisance, but that's physics, right? Causality has to be respected. If you violate that, then you have luxuries, but life is causal, right?
It doesn't violate or create so much of headache in the particle
For
world.
calculations, but
For
the real
particle,
life.
no, in particle world, it doesn't create that much of headache and you
Yeah,
obey
good.
causality. But in electrodynamics, it does.
No, I think that's because you create new things like time ordering, which is a
They
prescription.
create time ordering
But
here.
that's a prescription, like for respecting causality in many ways. I think so. So yeah, I think it's or Feynman-Green's functions, the
Or maybe
ways of doing the same thing.
another way of me saying it is that quantum electrodynamics is easier than classical electrodynamics.
No, that's because you deal with perturbative, like the first order. Here we are doing non-perturbative.
What is it?
We said we wonder what your dinner table discussions are like. Because if this common like at home life? Like do y'all just think you're not necessarily bicker about the nature of the mathematical foundation of physics, but
Always have somebody to discuss it with and.
I switch off. I switch off. Like unless like it is on the board, I try to. But I don't have the luxury to get out of the conversation most of the time.
it sounds like he doesn't have the luxury to get out of the conversation.
This is a matter of relativity.
Okay.
Yeah, later. When we have stopped recording. Yeah.
Okay.
Okay.
So yeah, let's proceed. Think let's. Okay. So So char is, I just take the whole thing, right? And remember, these are sum is integral is nothing but a sum. So each term I have to complex conjugate. Omega is real. So P, and now P of omega can be complex. So P of omega is, yeah, right, that's what it is. I can quickly immediately do one thing, that omega can be omega prime minus omega prime. And E omega is minus E omega prime. This is when omega is equal to minus infinity, omega prime is plus infinity. Minus infinity, D omega is minus D omega prime, 5. And exponential of omega will be minus. One more step maybe, now that it's an integral, this is a dummy variable, I can change the variable to omega, use the negative sign to change it, change the sign of the limits, so it was plus omega over 5 e raised to minus I omega b here minus omega. Sure. Right. These two look very similar, I can put it on one side. Fine. And that was the purpose of changing the limits. And this is these confused. No. Remember, we were looking for how does the Fourier transform look like in this. So if you have a equation like this, since Fourier functions are complete, this is, one should look at it as vectors. Each component must be 0. Right? So it is equivalent to saying vector A is equal to AI. So that's an eigenvector, and that is a summation over I. If A is 0, that means each component must be 0. So this is like an infinite dimensional vector space. These are the eigenvectors, that's the integral. So these are the components in the Fourier space. That means that P of omega should be equal to P of minus omega star. So the question was, how does a real function look like in Fourier space? It is a complex conjugate of, and it is an, let's see, I can say this more clearly maybe. So let's say, we write this as P of minus omega is P of omega star. Right. So if I were to think of this as a real and imaginary function, P of r minus omega plus I of imaginary piece here is equal to r omega plus minus I of imaginary part of omega. So what we are saying is that if there's a function that is real, if r minus omega, so the real part is even, and the imaginary part is odd. Or did I become small again? Okay, yeah, okay, it's readable, yeah. Okay, so if you have a real function in the Fourier space, its real part would be even, imaginary part will be odd. So that's a feature that we can use in a sense. Mainly we are interested in this dielectric, the susceptibility function. We will say it is real. That means it will have these features, or at least we can invoke those features in there. So that's a real part. And then there was one more thing I wanted to say. If the opposite of this, right? What if it was odd function? How does it look like? And it's 2:30. I'll try to wind up.
That clock is an
Oh,
hour back.
I see. Yeah. So it's hour back, yeah. So then it's it comes. Okay.
But nothing of this bothers you, Wes.
No, actually, I'm sitting like I'm tying that in because that relates to cosine and sine being even and odd, right?
Yes. Yes. Correct. Yeah.
So
Often you will write this in that form also.
It's just decomposition of frequencies into those
Correct.
waves.
Yeah.
Yeah. So which waves will contribute? That's what.
So is an odd function going to be imaginary then?
Odd function will be imaginary. Yes, that's correct.
Because odd times odd makes
Yeah.
even times odd makes odd.
Right. And I'm building small pieces to it, and in a single go, everything will come out in a few minutes. So just
The
Oh.
same applies for magnetic, is it?
so this is nothing to do with susceptibility. Any integral of this kind, for example, signal, whenever we are doing
Signal processing.
signal processing, the signal comes from the past, so this applies there. Where else? Signal processing is what I'm familiar with.
So
I
when
think
it's magnetic,
Yeah, go ahead.
when it's magnetic on the left, what will it be? P, the same P.
It won't be P. There it will be magnetic moment. The magnetic moment. This will be the magnetic susceptibility. This will be the magnetic field.
Oh, yeah.
The magnetic moment, right? The standard magnetic dipole moment.
Okay. Yeah.
Exactly the same thing goes through. There's nothing.
Yeah.
You can couple the two, like what probably you're thinking of is in the topological sense. Can P get affected from the electric field? From the magnetic field. So this is dt prime, and then you say this is a new response function. You bring it, and that is the axion response, but that is not traditional. Like that's what you invoke in topological insulator.
Yeah.
So I think that's what you're probably asking, but I'm not doing that. And that is written as a step function because it has all the features of the step function, like it's a constant. Yeah. So, one more thing I want to do. And that is if it is odd, right? Yeah, if P of, let's think of F of T, right? I want to keep F of T. And it applies for any function. If F of T is equal to F of minus T, right? How does it look like in the Fourier space? Do the same thing again. I will try to be quicker. E F of omega minus T. So this is minus 3 plus infinity. you just replace t like this. It is I omega. Omegas. But again, you do omega to minus omega prime. This flips, but then there's a negative sign. It comes back and you replace this to minus, this to minus omega. I did that all in the head. Is that okay? Okay. And now you can again say that again you have to bring it out to the left and argue, but it is clear that so this is f of omega is equal to f of minus. So oddness in a function in Fourier space is exactly the same. It is odd in Fourier space. Okay. So those are the warm-up exercises we need, and now we actually go to the chi. That's susceptibility. Any questions at this stage? Yeah, so we are interested in chi of omega, like in the Fourier space, and that is equal to p. P, okay, p, instead of p. F of p. Remember, f of p is the susceptibility in the absence of causality. Sense. And maybe I'll do this. Maybe 1, 4, 5. It will come out the same, but let me just minus. Right. So, okay. So. Very similar to what we did in the first piece. This 5. But the integrals are coming out differently. What frequency is set equal to the other. I have only one delta function, so only one integral can be done in here. So it's minus plus infinity 1 to 5. And let me write this as, let me keep omega 2. And I'm going to replace omega 1. Omega 1 will be equal to omega 1. Omega minus omega 2. 2 pi cancels out. So it's omega. So notice it almost separated out as far as the response went, but the dielectric function itself, now which was local, has gone into the frequency space and become local. So this is the price you pay. And but now we can use causality in here, right? So this is our first step. Again, no space, so I'm going to erase this and put this back. This is equal to -2 of the omega prime of 1 right? So okay. We know this. This is nothing but pi omega, right, in Fourier space. So put that in now. Minus infinity plus infinity omega 2 over 2 pi delta omega minus omega 2 plus I. This would be omega minus omega 2 4. And I'm not explicitly writing delta. Whenever I see delta, that's a delta limit. Delta tends to 0, right? So the whichever equation you see delta, it's understood that delta has to go to 0, and we are not being careful at what stage it should go to 0. So usually at the end. So that's this is F of omega 2. And this is how you have the first integral, which is as it seems like it looks like real part, but it's not, because this is not clear whether it is real or not. That has a complex and or real and imaginary part in that. So first integral is doable. So it is 1 over 2 f of omega 2 or omega, right? Omega gets replaced with omega. So right, and the second integral is just pi over pi. Let's run this. Oh, sorry. So let's just putting together whatever we had, except for the fact that we didn't, yeah, let me not say anything. Let's just say, what is the imaginary part of let me see what that is.
Well, you said you cannot say anything about function f, so I don't know how.
Or yeah, hold on. So remember, chi is real, right? So if chi is real, chi of r is even, right? Is even, and imaginary part of is r. Agreed? If chi, so this is susceptibility. It is real in the normal time space. So imaginary part has to be r. So let's So let's require that. And let's learn what we get. Yeah, so let's just substitute chi minus omega. So 1/q f of minus omega. Yeah, this is having both real and imaginary part in here now. And and is this by any chance real, or can I argue something here? I don't know, right? I think so now. Yeah, I go back and remember I have this freedom here, right? I can argue whatever I want about f. Let me require f to be odd. I don't lose any information with that because it is 0 anyway on the other side. So at least it's a allowed thing, but it's a choice you're making. So you have to come back and look at, is this really disturbing anything? So that's another exercise for another time. But I'm going to use that here, that I'm going to say that f of t is odd. Reasonable. And if f of t is odd, we showed that in the Fourier space also it is odd. In the total sense, not just real and imaginary. So the condition I'm going to use is require f of t is odd, right? That means f of omega is odd. Right? Which means that real part of f of r is equal to 0 and imaginary part is not equal to 0. Right? Because we argued that, why did we? Because the same feature shows up here, and because f has to be real also, right? Or no, f of omega doesn't have to be real.
This real part of omega, you're saying f of real part of omega is 0?
Yes. Is that clear? Oh, that's because
Yeah, just because of the odd property, right?
right? Yeah, that's all that is needed here. So real part of f is 0. Agreed? So now I can immediately doing that, I can conclude that maybe so real part is 0. So this is having only a, yeah, so then as well.
If you introduce negatives everywhere, then
Yeah, like I want to write f of omega as I times something. So let's say imaginary part of it. F. How I write that? So that I pull out the I. Because otherwise it gives you a feeling that this is the imaginary part. Actually, this is the real. Right? So I want to bring that out. So write that explicitly in there. So this becomes integral minus of minus infinity to plus infinity d omega q over 2 pi and omega minus omega 2 over plus delta square, and this will be written now as imaginary part of f of omega 2, and this has plus I times 1/2 and imaginary part of and this clearly says that imaginary part of chi is f of omega itself, as if causality is not there. Right? F is the susceptibility in the absence of causality, but then the real part of chi, The real part of phi is just this piece, right? So you would say the real part of phi omega is equal to minus notice if you know one, the second side is calculated from the real part. It's imaginary. Omega. And the imaginary part of omega 2 is this whole thing is the imaginary part of chi also, so it is 2 times. So f of it's 2 times, so it is 2 times. They allow me to write this 2 times imaginary part of the phi. That clear? And maybe a right? Is this imaginary part of phi? The way this expression is what is called the Kramers-Kronig relation. It tells you that if you know one part of the susceptibility, the other part is dictated by a mathematical relation. You can invert this also, but we won't go there. Now you can write the imaginary part in terms of real part also. The next, I have 4 minutes. I will do this for a very trivial example, almost trivial, which is what in real life it will look like. By the way, I should say that a real part of susceptibility is what is refractive index. It's a square root of refractive index. Yes. No. Square root of phi or epsilon, right? Square root of epsilon is the refractive index. And the imaginary part is the absorption coefficient of the material. What frequency it absorbs is decided by this. Water is a very classic example. Like, I don't know whether you're familiar about this or not. We have a whole optical spectrum ranging from minus infinity to plus infinity. If you think of it in frequency space, small frequencies are high in energy. Think of gamma rays and all the way to radio waves. Water is transparent only to visible light. I don't know whether you're familiar about this or not. If you go anything like imagine you are 100 meters below the surface of water, or for that matter, under a swimming pool, and you want to communicate with that using radio signals, gamma signals, X-rays, anything, nothing goes, only visible light. That's a holy luxury you have. So this becomes a big challenge when you're having submarine communication. So how do you communicate with them? It becomes that big challenge. And life itself is it's not surprising that life picked this because light, like why do we have sensitivity only to visible light? We don't need anything else because if we evolved in water, there's no other signal that can reach that. So we never
Or at least to the species that came out of the water.
Yeah, assuming that you all evolved from water. So that's it. Or another way of arguing is that you can say that this is an indication that
Isn't there something like they have found life thriving on that does not depend on light at all, very deep in the ocean? Isn't there something recent?
yes,
right?
the sulfur hydrotherms, right?
Mhm.
So there is life around hydrotherms, correct? So yeah, it will be good to see how their eyes have evolved.
Like it will
Sorry. I think the creature's called like the tardigrade or something
Yeah,
that lives on in the hydrosulfur bottle there.
Vents, yeah, we'll call it, yeah. Hydrothermal vents, but you're saying correct.
So the question and like the question, a related question will be like, well, how do they see? Like it doesn't need a seeing eye, right? Basically,
Yeah,
but
temperatures. And yeah, but I just want to do one more example because that will be, that will justify my thing that these are dielectric models. Right, so I just want to do one simple example, and most of the realistic examples are based on this. You just do many frequencies, and you just add them up. That's the basic, very trivially speaking. That's what you will do. Okay, so very quickly. Any questions, Venkat, Devendra? Too late for never class. Both of them actually. Okay, so let's say f of omega is just, it responds only to one frequency. Mathematically speaking, it's a delta function, right? So let's say some delta of omega, some special frequency omega naught. Like think of a creature that can sense only green light, like something like that. So that's fixed. That means imaginary, or it has to be imaginary, right? So it has to be having nine. But so I should have
Yeah.
I in there, and dimensionally I'm okay. Is it F has so these are this is dimensionless, this has dimensionless. Fourier space, I need a 1 over omega. Yeah, it seems that's 1 over omega, correct? So I think it's dimensional here also. Oh, okay. And so imaginary part is just delta omega. So then you know what real part of chi would be. So real part of chi, or first we'll say imaginary part. Imaginary part of chi of omega would be equal to 1 by 2 times delta omega minus omega naught. And the real part of chi of omega is equal plus infinity omega 2 over 2 pi and omega minus omega over plus the square and imaginary part. So that cancels out and you have delta of omega minus no, omega 2, right? Omega 2 minus omega naught. So wherever omega 2 comes, I have to replace it with omega naught. So it is 1 over 2 pi omega minus omega naught over omega minus omega naught square plus delta square. At this stage, as far as I'm not very close to omega, I can even pretend that these two can, like, if it is not zero, if, at least for omega not equal to omega naught, this is equal to 1 over omega minus omega naught. So this is if omega is not equal to omega. No. Right, so that's your frequency response in a sense, and this is realistic. Notice the imaginary part, that's the absorption coefficient. So this looks like this, and so this is the imaginary part, and the real part. I will plot that if I think, if I'm not wrong, anomalous, right? Yeah. So
Isn't there a sign missing somehow?
am I missing something? Oh, there's the minus sign. Omega not minus, so that might be the value that would flip it. Yeah,
Like
because
it
yeah,
is generally shown as sign
Yeah,
of omega or something.
no, this is minus, right? That's what you're saying, minus?
Mhm.
Like this is minus and this is minus. Because if I were to plot this alone, this will be like this, right? 1 over omega goes down. And then I connect it back. So this is opposite to what this is. Right? So it is exactly negative of that because I just remember it. this doesn't involve dissipation yet. So the next thing what one can do is, what if you have dissipation in here? And the standard thing, the most popular dielectric function is the Lorentz Drude model, and it is 1 over omega square plus qi gamma plus omega naught square. Right? So currently there's omega naught square that is kept. So now we want to put an imaginary prime talk about, and that will be the Drude model. I think Venkat, you were inquiring about that. So that will be putting this in here, the right piece, so that you get the correct form. Yeah. So, but this is the idea that you put some model in here, get the real part accordingly.
So why this specific
Why what?
I times?
Oh, yeah, I can motivate that in a minute. Yes. Yeah. So, yeah, give me a second, I'll motivate that. But any questions on this? I'll already erase the board for that. Any questions on this? Yeah, why that specific? I'll give that answer in a minute. Yeah. Any other questions? Comments? Okay, so quickly, why is Drude model so popular? So usually what you do is, now you want to yeah, so you have a material, let's say. So this is modeling modeling susceptibility or dielectric functions. Dielectric functions are the same, right? And the idea is we are interested in polarization, correct? So that's polarization, and that's a vector. Polarization in many ways is nothing but at any point, how much is the charge and how much does the charge displace from its equilibrium position. So in many ways, it is some charge Q times R, right? It's a position dependent quantity. So that's sort of the dipole moment, if you want. So this is a dipole moment density, if you want, not just dipole moment. Is that clear? That definition? Right. Venkat, is that?
Yeah.
Okay. If you allow me to do that, so now this is the position of the charges at a certain point. So if you have a material, you have usually atoms, right? Plus and minus. So these are plus, minus, plus, minus. So there's a lot of atoms, and we want to talk about what is the displacement of the atom from a certain point. You would write what decides that. This is a model. It's not a fundamental model. So you write Newton's laws, right? So mass times acceleration of a charge inside this one particular electron in that. So this is the acceleration of the electron, Newton's law, right? So it's the simplest model you can keep. Now, if you were to exert an electric field, what are the experiences left? The force will be just charge Q times the electric field itself. That's one thing. If it is inside an atom, there are many electrons that does not want to move around. So there is a force that wants to keep it to itself. So that's like a spring force. So this is a model again, remember. So there is a spring constant. You model it. So that's minus of K, but you want to model it as, yeah, K over M, right? So this is K times some R, right? How much you pull it away from the equilibrium. So that's a spring constant. If the electron is moving, then you would say that is a friction, like it's a velocity dependent force. So you would say that is friction. So this is gamma, or let's say B, right? B over velocity dependent force, right? So position dependent force, velocity dependent force, there's an acceleration, and all this is driven by the electric field. So that's the simple model you have. And put this in Fourier space. In Fourier space, you go to Fourier space by simply taking the time derivative to I times omega. So that's a frequency response. Acceleration is 2 time derivatives, so there's a square minus omega square. So minus omega square, and there's a mass. I will put that in the denominator. So that's Q over omega square times position, right? That's time derivative becomes omega, and then that is R. Right, that's equal to Q over M times the electric field, this time in the Fourier space, right? This is in omega space. And K over M, I will say, is frequency squared. That's the binding energy of the atom. So B maybe square R, and B over M, I'll call it gamma minus gamma, but there is an I that comes in, the I and the position is off. So you see that this equation takes the form omega B squared plus I omega I gamma minus omega squared times R is equal to Q over ME times an electric field. So if I'm interested in the polarization, I have to substitute this back in here. So a simplistic polarization model that takes care of a material would be Q, like Q square, right? So this is Q square over ME. And then there is an electric field that is the response. And this is omega B squared plus I gamma minus omega squared times the electric field, which is the driving quantity. Remember, polarization is something times the electric field. That will be the susceptibility in this simplistic model. Now, what is a dielectric and a conductor? If this is dominating, that's a conductor.
No,
That's a plasma model you're talking.
okay.
So if this dominates over, like insulator, you can think if this dominates, this is like here you can see, right? Omega B is the spring constant. If this dominates, that means the electron is not allowed to move anywhere. It stays with the atom, right? So that means if this dominates, that's an insulator. If it is able to move around a lot, this is more dominant over the binding energy, then it's a conductor. But there's also one more piece, that what if the inertia is very large, right? For example, if this term dominates, that is the acceleration term dominates, that's not usual, that's a plasma. So there are 3 pieces in here based on which dominates, you will call it 3 models. So when the conducting piece dominates, you call it a Drude model. When the binding energy dominates, you say it's an insulator model, and if this dominates, it's called a plasma model. So that's the 3 models that you come up with. When it's a graphene, it is having this structure in here. Like I think you have dealt with graphene, Venkat. So there it is, the conductivity piece shows up only this piece. So which is kind of nice. So that probably helps you with the construction.
And this is only for one electron, so in principle, you will create it for an oscillator
Yeah.
model for all the electrons, summing over things and all. That's how you calculate your.
So when you want to make it more realistic, what Prachi is saying is that there are multiple of this. So that's how you make it more realistic. And they do a good job, like usually, again, by good job, you mean 2 significant digit is a great thing in this case. Like 1 significant digit is already big, but if you can reach 2 significant digits, it's remarkable, usually. Like zero is sufficient to have a discussion. So that's the state of art in a sense. Yeah. Pretty. There's a lot of room to explore that. And this is a very simple model though. It is classical, right? Newton's law, and you can try doing quantum mechanics. It doesn't change much. You'll still be on the same.
But it is still a classical model.
Yeah.
You would still call it a classical model of susceptibility.
Yeah, that is all I have. So now we have an idea of what susceptibility is. Susceptibility is the input, like that's what you'll say. There are two susceptible materials and what happens. So the next time onwards, we can proceed forward like this. Right?
So this again. So I can't use this for magnetic, right?
The same, okay. This model will not go for magnetic, right? Of course not. For that, you have to use which type of magnetism you're talking about. In magnetism, you have ferromagnetism, and whatever we use in Casimir context, it is usually the diamagnetic materials. And most of the time that magnetic materials that are used in the lab that are ferromagnetic. So you want to be careful which one you're using. Ferromagnetism has a nice feature because temperature dependence has interesting features in there. There is a Curie temperature, and there is a lot of interesting features that goes in. But it can be accommodated easily here. But then
Within the Lorentz model.
Yeah, go ahead.
You are saying that can be accommodated within the Drude-Lorentz model.
No.
No.
No. It can be accommodated as a model separately, as a Curie model. A Curie's model is what is popular there. But a small comment there, in Casimir physics, it is diamagnetic materials that are coming into picture. So you want to be careful how much you can accommodate ferromagnetic materials in there. Yeah, so you won't see too much literature on ferromagnetic material in Casimir physics. So yeah, there is a separate model called the Curie model, but it's not useful, I think, in this context. Probably, yeah. Yeah, and then there are other materials like superconducting materials. There you have London model that comes in. So all those are interesting, and there are literature based on superconducting materials interacting as a Casimir effect between those materials. So all those cups at this stage, this is where you would model. But most of what we will be doing will be independent of all these models. We can use any model we want to at that point. So I'll stop talking about models for a long time after.
Yeah.
And whenever you will see a susceptibility, it will be understood that it will obey Kramers-Kronig. So the whole causality is inbuilt, saying that this has to be satisfied. That's it. From that point on, I won't worry about causality after that. So it is implicit in that. Helps. Okay. I think we should stop. Rashi, questions?
Yeah, no.
It's a Friday.
Probably already late, right? We were supposed to end early.
But that was 4 o'clock was us being committed to it, so that should be a planned thing. But yeah, I guess
Should I stop the recording?
yes. You can stop and still we can be available.